Well, hi there, Nick here, M0NTV, and welcome back to my shack and to another video. And apologies that this one's taken a bit longer to get to you, but I've been away on holiday and just life really getting in the way of home brewing and amateur radio in general. But what I want to do today is to pick up on what we started last time, and this was a mini series really on some of the challenges that we face when we're trying to build simple transistor amplifiers, small signal amplifiers for RF. And I built a simple little one with just using one 2N3904 transistor, and this is the same design we're going to be looking at today from a different perspective. Last time we were looking at the challenge of beta, the gain, the current gain of the transistor, and how this varies over frequency and the challenges that presents to us when we're building for HF. If you think that's bad, meet what I like to call the curse of capacitance, and that's what we're going to be looking at today. I'll explain it all to you as best I can. Just to say, I'm not an expert in no way, shape or form. I'm just fascinated with this stuff and like to share some of the stuff that I'm learning and experimenting with myself. And I do that in the hope that it will be helpful and useful to you. So thank you for watching. If you enjoy this video, then please like and subscribe. And I hope that you find something useful and of interest here. And as always, I hope you enjoy. So I have my little amplifier set up here. It's powered up. And actually, if I just pop round here, you'll see, yeah, it's drawing about 12 milliamps. And it's open circuit on the output, okay? And the input is going round to my nano VNA. So I'm just showing you now the screen of my nano VNA, and I'm sweeping from 1 megahertz to 30 megahertz, and I have two markers, and you'll see marker number 1, as I've got up at the top here, is set at 7.090, and marker 2, which is right the way over here, is set right at 30 megahertz. Now if you look at the resistance, which is what we're looking at here, so just the resistive part of the input impedance, you'll see that at, well, 40 meters we are 74.8 ohms resistance, but at the top of the 10 meter band we're 32.2 ohms. So not too bad at all really. That's not the problem though. The real issue is when I show you the reactance. So this is now just the imaginary, the reactive part of the input impedance, and you'll see at the top end at 30 megahertz we've got a slight capacitive reactance there, -9, but look at this, down at 7.090 we've got -74 ohms of reactance. So this is all capacitive reactance, and you'll see actually if we were to go lower it gets worse. The capacitive reactance increases, and so you know this is going to present us with some challenges. First of all, in terms of impedance matching, because even if we manage to match the differing amounts of resistance on the input, if we're trying to build a broadband amplifier for the HF range, then obviously that's got some challenges, but we're really going to come against it when we try and deal with this reactance, because this reactance by very nature varies with frequency, And what's happening here is we are capacitively loading the input of the amplifier. Now this will have a number of effects. One will be it will reduce the input impedance, and that will unfortunately mean that we will be asking the signal source that is feeding into it to provide more current than it's probably wanting to provide. So we're not going to get the full amount of our signal getting into our amplifier. Some of it is going to get lost on the input because of this capacitive loading. So in other words, the capacitive loading is making the input impedance of the amplifier look smaller, and because it's a smaller impedance, less of your signal will be dropping over the load, your amplifier, and more of it will end up being dropped over the internal resistance of your signal source. So you're just not getting as much signal into the amplifier. Now the question you're probably asking is the question that leapt out to me at the time, which is, where is all this capacitance coming from, right? Let's dig into it and find out. Now the answer to that question is not as immediately obvious as you might think. The truth is, whenever you build anything homebrew style particularly, and this is my little amplifier, whenever you do anything like this, you will get parasitic capacitance, otherwise known as stray capacitance. And this is just the effect that you get when you have two conductors at different voltage levels, and an electric field exists between them and energy is stored, and that's capacitance. And so this can be how close you have one component next to another. It can be the lead lengths and how high a component is from the ground plane. All kinds of different ways in which stray capacitance can creep in and make a difference in our calculations and the performance of the circuit. But actually, if we want to find the source of this particular capacitance that's troubling us here, we have to go much deeper into the actual construction of the transistor itself, because the source of this capacitance is actually an intrinsic capacitance within the transistor. So let's have a little look at the basic structure of an NPN transistor. So there's the familiar schematic there with the base, collector and emitter terminals marked. What it actually looks like in simplified form inside is something a little akin to this. So I've marked the three terminals there with my oversized cursor here, the collector, the base and the emitter. And what we've got essentially is three conductive areas. We've got an N area, a negative area. We've got a P, a positive area, and another N negative area here. And it's a little bit like a sandwich, really. You've got two slices of N bread with a nice dollop of P positive in the middle of your sandwich. Now there is a point at which these areas start to interact with one another. It's called a semiconductor for a reason, because under certain circumstances these areas are separate, but apply enough bias current to the base and things start to happen, and charge carriers, electrons and holes start to move between some of these areas given the right condition. And what this means is that you've got a conductive surface here, and you've got a conductive surface here, and you've got another conductive surface here. So if we just look at the top here, between the collector connected to this top N and the base connected to the P in the middle, this part here, you've got a conductive surface here and a conductive surface here, and a gap, and that gap may be empty space, it may be filled with something else, as it is with the transistor, but two conductive surfaces with a gap in between, different voltage, you've got capacitance. And so this is indeed what happens. So between the collector and the base is a capacitance, just because of the design of the transistor. And of course, you won't be surprised to hear that it's just the same between the base and the emitter. There is a capacitance that exists there. Now, let's draw that in on our schematic. Now, obviously, this is not a real physical capacitor attached, but it's behaving as though it is. Well, okay, so we've got that capacitance there, and we call the capacitance between the collector and the base CCB, collector base capacitance, and the capacitance between the base and the emitter CBE. How much capacitance then is a good question to ask, and for this we need to look up the data sheet. Well, actually, helpfully, these values of capacitance are usually recorded in the transistor data sheet, and that's certainly the case for the 2N3904. So here's the data sheet, and actually when you scroll down here, you get down to here, down here, just underneath the transition frequency. So we've got what they call C sub CBO, the collector to base capacitance, and that's 4 picofarads. And then underneath that, the C sub EBO, the emitter to base capacitance, and that is 18 picofarads. So let's put those values now onto our transistor. So back to the schematic, we'll put in the 4 picofarads, which exists between the collector and the base, and the 18 picofarads between the base and the emitter. Now you may be tempted to say, big deal. I mean, so what? So we got a bit of internal capacitance. And you may be tempted to think, well, we probably need to worry about this one more between the base and emitter, because that's higher than just this 4 picofarads between the collector and the base. But actually, it's the other way around. And that's because there are certain circumstances which will mean that this tiny amount of capacitance will appear much, much larger and will cause us difficulties. And that is what we're going to explore next. Now, just to say, we are going to get into a bit of very basic small signal analysis in just a second. But if you're looking at this independently, you might find very often that this CCB, the capacitance between the collector and the base, is sometimes referred to as C mu, the Greek letter mu, and the base emitter capacitance is sometimes referred to as C pi, just in case you come across that. Okay, so how then can 4 picofarads cause us so much problem? Okay, well, we're going to ignore the 18 at the minute because that's not going to particularly bother us, because you will remember that my design is a common emitter amplifier, which means we put a signal on the base and we take it at the collector. So it's this junction which is the important one, and for other reasons which we'll see in just a moment. So let's see why this 4 picofarads is such a big deal. Okay, where the wheels fall off. It's something called the Miller effect. So here is our transistor, and let's draw in just the collector base capacitance, this CCB or C mu as it's sometimes known. Now my amplifier, as I said, is a common emitter amplifier, which means we put a tiny signal, and let's say this is a voltage, a sine wave here on the base, and then what we get, of course, is a much larger signal on the collector, but a much larger inverted signal. So just check this out. So the peak here corresponds to the trough here, and the trough here corresponds to the peak here. So in other words, the output is 180 degrees out of phase with the input, and that's because a common emitter amplifier is an inverting amplifier. Big deal. So, you know, we all know that. What's the problem? Well, the problem is, from the point of view of the bass, this signal here creates a voltage drop over this internal capacitance, this 4 picofarads. But because of the amplifying effect of the transistor, which makes this signal much larger than this, these little voltage wiggles here are not very big, but they're a heck of a lot bigger over here. So there's more voltage being dropped over this internal capacitance. So the bass, as it were, looks at this capacitance and says, whoa, where's all this voltage come from? Look at all this voltage. Well, I haven't got it. It ain't come from me. Look at my voltage here. I've only got a little bit there. Where's all this voltage drop from, right? It must mean, wow, that capacitor is a lot more beefy and bigger than I thought it was. And really, this is what's going on. The bass is kind of seeing the voltage drop here and misinterpreting it as meaning that this is a much larger capacitance because it's not taken into account the amplifying factor of the transistor itself. So just to be clear, it's this changing voltage on the collector which is really causing the bass to get very confused, because it's seeing these huge big voltage swings, dropping voltage over this capacitance. It can't account for it itself. It's not factoring in the gain of the transistor, and so for all the world it looks like a much larger capacitance, and hence the Miller effect. So what happens is, and CM is this Miller effect. So what happens is, the Miller effect only really comes into play when certain conditions are met. Now, one of those conditions is that you have an inverting amplifier. The other condition is that there's a fair bit of voltage gain in your circuit, because this makes, obviously, the wiggles here look that much bigger here. And actually, if there isn't as much gain, there's not as much voltage dropped over here, and you don't get this kind of amplifying effect, which I'm going to describe to you in a moment. So the way that the equation goes is that the actual capacitance that this looks like, this Miller capacitance, is the real capacitance, 4 picofarads, multiplied by 1 plus AV. Now, AV is the voltage gain of your amplifier. Now, this, not the beta, right? The voltage gain of the, so that will depend largely, I mean, the rule of thumb, if you can imagine the full circuit with all the resistors in, is if you've got a resistor here on the collector, you've probably got a resistor here on the emitter, and you divide the collector resistor by the emitter resistors, and that gives you basically the voltage gain. So let's say if you had a voltage gain of 10, right, for instance, so the Miller capacitance, so the capacitance that the bass thinks it's seeing would be this real capacitance, 4 picofarads, multiplied by 1 plus 10, well, 1 plus 10 is 11, and 11 by 4 is 44. So instead of being 4 picofarads, it would look like 44 picofarads. Now, that's quite a lot more, but it gets an awful lot worse if you've got more gain, because obviously it's the gain that's going to be multiplied by this. So in my circumstance, if you can think back to my little original circuit, but actually I have got an emitter resistor, but it is fully bypassed by a capacitor. So the only resistance which the emitter is seeing really is what we call R sub E. So that's the intrinsic resistance at the base emitter junction, which is very low. It's based on the thermal voltage. It's a very low amount. In my case, it's 2.5 ohms. So that means my much larger collector resistor is being divided by this tiny amount. So actually the voltage gain of my amplifier is something like 220. It's minus AV because it's inverted, because we're taking it at the collector. 220. So when you plug that in, the Miller capacitance for my design comes out at 884 picofarads. So what looks on paper like just 4 picofarads, what difference is that going to make? Actually, in real terms, when this is plugged into my amplifier, it ends up looking like 884 picofarads. That is a huge amount, and particularly, and this is the third kind of thing about the Miller capacitance, at higher frequencies. Because, the higher in frequency you go, the more quickly capacitive reactance decreases. And that's the kicker, really, because if we did only have 4 picofarads, if there were no Miller effect, when you work out the capacitive reactance for that, actually you get a big figure. It's 5.6k ohms, which when you parallel that, as we're going to be doing in a moment, with the resistive part of our impedance, it's not going to make a difference. But at 7 megahertz, with the great whopping 884 picofarads that we've got, that is quite a low amount of capacitive reactance. And the higher in frequency you go, the lower that capacitive reactance becomes. And so it dominates the input impedance and brings it right down. And that is precisely what we're seeing in my amplifier. And we'll dig into this in just a moment. And so that's a problem because my amplifier ticks all 3 of those boxes, right? It's an inverting amplifier. It's got a high voltage gain and I'm using it at HF frequencies. So that's why I've got such a problem here. Now, let's just have a little look at this from a small signal point of view. Now, don't worry too much about this. I'm not going to go into all the details of this here. If you're interested, do go and watch my video that I made on simple small signal analysis. And this is using the hybrid pi model, which I used before. So you don't really need to concern yourself with the transistor part at all. Just look at the base section. Now, if we were calculating the input impedance of this design, generally what we would do is we would parallel 2 resistances. One is what we call RB, the other is what we call R pi. Now, RB is just itself the parallel combination of your 2 resistors in your base voltage divider, which in my case works out at 1.45k ohms. R pi is the small signal resistance of the transistor looking into the base. So basically what that is beta plus 1. So that's the current gain of the transistor plus 1 multiplied by this small intrinsic resistance at the base emitter junction, R sub E, that I mentioned, plus anything else that you've got hanging off the emitter which is not bypassed. So in my case, because I'm fully bypassing my emitter resistor, that's what it is. It's beta plus 1 times RE. So RE is 2.5 in my case. So at 7 megahertz, and if you need a reminder, just go and watch my last video where I talked about this, beta is about 29. So when you multiply that by 2.5, that gives us an R pi of 75 ohms. Right, so that would mean that when we're calculating the input impedance, we would take that and parallel it with that. So when you do that, so you take your 1.45k of your voltage divider network and you parallel that with the 75 ohms of R pi, that would give us an input impedance of about 71 ohms, right? Not too shabby. However, we've got to deal with all this extra capacitance that we didn't plan and we didn't really want. So that's the base emitter capacitance, 18 picofarads, you'll remember, but also the Miller capacitance now, which is this whopping great 884 picofarads. Now, in small signal terms, these levels of capacitance show themselves as capacitors to ground. And because they're in parallel capacitors sum together. So that means that when you do that, you get an overall capacitance of 902 picofarads. Now, to calculate now what effect this is going to have on the input impedance, we need to calculate what that looks like in terms of capacitive reactance at 7 megahertz. And there it is. So XC, capacitive reactance, is 1 over 2 pi FC. So 1 divided by 2 times pi times 7 megahertz times 902 picofarads gives us about 25 ohms. Now, that's going to be a problem, because now what we've got to do is we've got to take the original two resistances, but we've also got to now parallel in this capacitive reactance. And as you know, whenever you parallel resistances, the total resistance will be lower than the lowest value. So we're in trouble here, because when you do that, actually that brings the input impedance down to 18 ohms, from 71 to 18. So you can see the dramatic effects that the Miller effect has on my common emitter amplifier with a big voltage gain, using it at HF. Now, you may wonder why there is such a discrepancy between the results that I got on the Nano VNA and the ones that I've calculated myself. When it comes to the resistive part of the impedance, of course, it's a pretty good match. I mean, I think it was 74.8 ohms resistance we measured at 7 megahertz, and 71 ohms I calculated, so that's really very impressive. But where the two diverge are when it comes to the capacitive reactance. I calculated here down the bottom left 25 ohms of capacitive reactance as a result of the Miller effect, and I'm getting something like 75 ohms on the Nano VNA. So there's all kinds of reasons why these figures can be different. Bear in mind that my calculations are assuming certain things. They're assuming that the capacitance between the collector and the base is indeed 4 picofarads, as the datasheet suggests, but the datasheet is produced by a company that certainly didn't produce the transistors that I purchased, so who knows? My individual collector base capacitance on that particular transistor may be more, maybe less, so that will affect things. There may also be other capacitance, other stray parasitic capacitance knocking around that I've not even bargained for in my own calculations. So there's going to be a bit of difference, but don't let that trouble you too much here. Really, what I want you to see is the overall effect. But I think it's undeniable that this capacitive loading of the input impedance by the Miller effect is a big deal and makes a big difference. So what can you do about this? Well, largely, I guess there's two directions you can go in. One is to try and tweak what you've already got. And there is a way of counteracting the Miller effect, which weirdly enough, and this is really counterintuitive, involves soldering in an actual physical capacitor between the collector and the base. Now you might think the whole problem we've got is capacitance between the collector and the base. Why would we want to add more to it? But actually, I think it's about kind of swamping out that original 4 picofarads with a slightly larger capacitor. But it doesn't have to be very large. I mean, I used a 10 picofarad capacitor. So let's have a look at what happened when I did just that, when I soldered in a 10 picofarad capacitor between the collector and the base. Okay, so this is the amplifier now. It's switched on, powered up, open-ended on the output as usual. But just notice I've now soldered on this 10 picofarad cap, which hopefully you can just see, between the collector and the base, hopefully swamping out that intrinsic collector base capacitance, right? So that's what the circuit looks like. Let's go over to the nano VNA now, which it's connected to, and check out what we're reading. So you are looking at that same sweep, 1 to 30 megahertz, markers in the same place as before, and you're looking at the resistance. But look now, look where the actual resistive part of the input impedance is now, 20.6. So it's dropped right down. So I mean, it's a lot flatter. So there's I think it's 12.7 ohms at the top of the 10 meter band and 20.6 at 7.090. So that's certainly flatter there, but it has reduced the input impedance. Let's have a look at the reactance. Now that's certainly a lot better. It's a lot flatter, and you will see that the difference between those two markers is a lot less. Now this curve is still here, but note the curve has been pushed lower in frequency. So actually from this point on the 40 meter band here upwards, it's pretty flat. So, you know, that's certainly more usable. But of course, it means we have got a much lower input impedance. You could fix that with some impedance matching, like a transformer or something like that. So it works, but as I said, no such thing as a free lunch when it comes to RF electronics. So then I thought, well, how about approaching this problem from another direction? Because one of the conditions of the Miller effect is this high voltage gain. So what if I did something about that? Because there are other ways of introducing feedback, and one, of course, is emitter degeneration. Now, I have an emitter resistor, but it is fully bypassed with a capacitor. But it doesn't have to be. So what I could do was lift that end of the capacitor, the end that goes to ground, and insert in there a small low-value resistor, like a 10 ohm resistor. And so that then would mean that even at AC, there would be some more resistance on the emitter, which means when it comes to the voltage gain, it wouldn't be 550 divided by R sub E, 2.5. It would now be 550 divided by 2.5 plus 10. So that will bring the overall voltage gain down. It will also have the effect of increasing the input impedance, which is kind of what we need. So that's what I tried next. And so what I have done now is I have lifted the leg of this emitter bypass capacitor, this leg that was connected to ground, lifted, raised it up, and then soldered in a 10 ohm resistor to ground, so that at AC now, the signal will see this additional 10 ohm resistance along with the 2.5 ohm intrinsic resistance of the base emitter junction. And so let's connect this up, power it up, and see what difference that makes on the Nano VNA. Well, as you can see, it certainly had the desired effect of raising the input impedance. So this is the resistance again, and you'll see that marker 1 now, we're up to 88.2 ohms of resistance, and 47, let's say, at 30 megahertz. So not quite as flat as it was with the 10 picofarad capacitor across the base collector junction, but not too bad. So let's have a look at the reactance. Oh dear. Just when you think you're winning. Now look at this now. So at 30 megahertz, we've got minus 14. So minus 14 ohms of capacitive reactance, but look at this now at 7 megahertz again, we're 135.4. So there we go. As always, you do one thing, it makes one thing better, but then it stuffs up something else. So such is the world of RF electronics. There's no such thing as a free lunch when it comes to RF electronics, because you have a problem, you fix that one thing, and then that creates other problems. You disappear down a rabbit hole for so long before, well, I start to think, I think I've seen enough here. So the second way of dealing with it is actually to say, right, maybe we need a different design. One that's not too complicated and too much of a kind of step up in complexity to the one that we've had, but one which from the get-go factors in dealing with the Miller effect. And that is what we're going to be looking at in the next video. I'm going to build a couple of different examples of slightly more complex circuits, but not too complex, that actually, from a design point of view, deal with the effects of the Miller effect, so that actually it doesn't rear its ugly head too much. So that's for next time. Thank you very much for watching as always, and for supporting the channel. Please like and subscribe, and if you've got any questions or comments, by all means stick them in the comments below. But until next time, look after yourself, and I will see you on the next video. Bye bye. 73.